topics all around how we interact with mixed reality systems. So taxonomy for AR interaction derived from the work in the past 5 years, user interface for one-handed discrete and continuous input in mid-air, a calibration technique for aligning tracked hands in see-through AR, and a reinforcement learning-based method for enabling mid-air text entry. And then finally, a predictive performance model for interaction tasks. So very cool. I'm very much looking forward to this. The first presentation on the taxonomy is going to be presented by Julia Hettel from the University of Hamburg in Germany. So please take it away.
Okay. Hello, and thanks for the introduction. And welcome to my presentation about a taxonomy of interaction techniques for immersive augmented reality based on an iterative literature review. I'm Julia Herde, and my co-authors and me are from the University of Hamburg in Germany. In the last years, we saw impactful developments in the field of augmented reality and sensor technologies. Nowadays, it is possible to precisely control a robot's arm by just using the arm and hand movements. In this video, we can see how even a robot's arm stripper can be easily controlled to grab fractal objects while force feedback is visualized in AR. Such and other interactions are possible due to precise sensor technologies, especially self-contained untethered headsets, various built-in sensors like head tracking, hand tracking, speech recognition, and even eye tracking, for example, on the HoloLens 2. Due to these recent developments, novel interaction techniques have emerged. So our goal was to capture and structure the current state of research of interaction techniques. We focused on immersive augmented reality, including head-on displays and projection-based AR, in a time frame from 2016 to today. To structure the current state of research, we developed a taxonomy, which helps to provide an overview about existing interaction techniques, as well as a common ground for discussion, by formalizing the scope and introducing consistent terminology. To develop the taxonomy, we use an iterative method. Instead of analyzing all existing interaction techniques at once, this method allows us to include batches of interaction techniques consecutively and revise our taxonomy in each iteration until ending conditions are met. For each iteration, the researchers can choose between two approaches. In the empirical to conceptual approach, existing objects, in this case interaction techniques, are analyzed, while a conceptual to empirical approach is based on previous work or the researcher's knowledge. Since we wanted to investigate the current state of research, we mainly focus on empirical to conceptual iterations. For these, we performed a literature review to identify interaction techniques and include them in our taxonomy. For the literature review, we searched for interact and augmented reality or mixed reality in the databases of IEEE and ACM. Initially, we found 2,100 results. To break them down into batches of interaction techniques to include iteratively, we grouped the papers by the venues they were published at. For each iteration, we focused on one venue, screened these papers, extracted the presented interaction techniques, and analyzed them to create and revise our taxonomy. In total, we included 44 papers from 6 venues. This figure presents our resulting taxonomy. Across all analyzed interaction techniques, we found 2 common properties, which we included as dimensions into our taxonomy: task and modality. For both, we identified multiple categories. Based on this taxonomy, we define an interaction technique to have exactly one task, which should be accomplished, and one or more modalities, which are used to accomplish the task. In the following, I want to present these categories, starting with the tasks. One basic task is creation, which is used to let a virtual object appear. We divide this task into subcategories based on the complexity of provided information. An activation is performed when the user does not define any properties of the object. It can either be used to let a hidden object appear or to create a new but predefined one. 2D drawing is used whenever the texture of an object is modified, while 3D modeling also allows the user to modify the geometry of an object. The task we encounter the most is selection. We found that the complexity of the required interaction technique mainly differs by the arrangement of selectable objects. For 2D selection, all objects are placed on a planar surface, for example, a grid-like UI, and a 3D selection is needed if the objects are spatially arranged. Geometric manipulations cover translation, rotation, and scale. They are often used and represent nearly half of the interaction techniques we encountered. Abstract manipulation is not that established in previous taxonomies. In our taxonomy, abstract manipulation includes all interactions which are not directly related to visualized objects. We found two common use cases. It can be used to change the internal system state, for example, to load content or to switch between modes. Or it can be used to interact with physical objects existing in the real world, like Internet of Things devices. Based on the input type, we identified two subcategories: discrete and continuous abstract manipulations. Finally, we included text input as a task, which covers all techniques that enable a user to enter characters, words, or sentences. To perform these tasks, there's a variety of modalities which can be applied. In the following, I will present the modality categories of our taxonomy. To cover all modalities where a user physically touches something in order to interact with the system, we introduced the category of tactile interaction. We identified three subcategories: touch, generic input devices, and tangibles. Touch includes all interactions where the user's hand physically touches a surface. Generic input devices cover all kinds of controllers, mouses, stylus pens, devices without a single designated function. In contrast, tangibles keep their specific function over a period of time and can represent a specific virtual object. Gestures cover interaction modalities where movements of a user's body are used as an input. Hand gestures are the most commonly used ones and are seen as a natural and intuitive way to provide input. We also found one occurrence of a face and one of a foot gesture. Furthermore, we encountered the modality of voice, which can be used in AR applications, since modern devices and platforms often have speech recognition capabilities. The modality of gaze is used to capture the direction user is looking at by either tracking the eye or the head orientation. Even though eye gaze can be considered as being more natural, head gaze is currently used more often. Authors mention different reasons. Head gaze is currently more affordable, since every headset can track the head rotation, but not every headset has built-in eye tracking. Also, head tracking was found to be more accurate. Brain-computer interfaces convert brain activity into commands to control the system. Since they can be used hands-free and don't require the movement of any body parts, they are particularly interesting. However, in our literature review, we only included one occurrence. This table presents an overview about the frequencies of combinations of tasks and modalities we found. The most frequent tasks are geometric manipulations, especially translations. Hand gestures is the most common modality, and the combination of using hand gestures for translation is the most common interaction technique we found. This table also shows which task modality combinations we did not identify in the scope of our literature review, which could give us hints about possible research gaps. Furthermore, we were interested in how modalities are combined in multi-modal interaction techniques. This figure shows all frequencies of identified combinations. It shows us, for example, that hand gestures are paired with every other modality except for brain-computer interface, and that hand gestures and voice and hand gesture and head gaze are particularly common. These combinations especially appear in selection tasks. A common pattern for selection is to apply a pointing technique, like gaze or hand gesture, to select an object, and a confirming action via hand gesture or voice. By developing the taxonomy, we also analyzed emerging trends about interaction techniques in AR. Today, I would like to present our most interesting observations. In contrast to virtual reality, the user's environment can be included in augmented reality settings. We identified two directions of how AR and the real world can interact with each other. AR can be used to manipulate the real world, which we introduced as abstract manipulations. And here AR can be used to provide a user interface, visual feedback, or even a preview of planned actions. Also, real-world objects can be used as input. A physical object can either act as a tangible and directly represent a virtual object, or provide passive haptic feedback. We also investigated which AR technologies are currently used and observed a clear trend towards optical see-through AR, especially in the context of untethered mobile headsets. Currently mentioned disadvantages of optical see-through are the limited field of view, as well as inferior retina quality. So with further technological improvements, this prevalence could even be strengthened. For tangibles, we noticed a trend towards everyday objects. Researchers include a variety of common objects into their AR applications, like photo albums, spray bottles, wallets, smartphones, things a user typically finds in their surroundings. Such interaction techniques mostly aim to facilitate the interaction with AR systems by performing everyday tasks without the need of additional devices. We also observe the goal of developing subtle interactions. This can be achieved by using minimal movements, like facial expressions, or by transforming the action space of hand movements to be smaller and more unobtrusive. For example, by performing gestures at the waist or wrist, or by directly touching the own skin. We also paid attention to which application fields are considered in the papers. The three most common fields we found are interactive data visualization, smart home, and the interaction of robots and drones. Interactive data visualization especially uses the property of AR to easily view virtual objects from different perspectives, either by anchoring visualizations to a tangible and naturally rotate and translate them, or by placing them in the real world and letting the user move around. Smart home, as well as robot and drone use cases, take advantages of the fact that both the real and the virtual world can be seen simultaneously. So in this work, we performed a literature review and developed a taxonomy of interaction techniques for immersive augmented reality. We identified and defined two dimensions, tasks and modality. In the future, this taxonomy can act as a guideline for developers and researchers to design new interaction techniques and also to identify emerging trends. Thanks for your attention.
Okay, thank you very much, Julia, for this great presentation. This is the first talk in the session, so just a reminder, you can ask questions either here through the chat. You can post them on Discord, please, and then they're going to be summarized and I can read them out. So I'm hoping to see some questions, but maybe to tide us over. You know, when I looked at the talk and at the paper, like I found it really, really interesting that you looked at so many works in the past 5 years. And I'm really wondering, you know, sort of as a summary and to help us digest this work better, when you look through the papers, what are the challenges that you extracted from them? Are there any patterns that the papers perhaps agreed or disagreed on where we should focus on more going forward to unleash even more potential?
I think a very interesting trend is the thing to have more unobtrusive interactions. So in general, to bring AR more into everyday context and to make it more easier for from a technological perspective to don't have a lot of required sensors or something, and even from a social perspective to have it more socially acceptable. And I think that's a really important and interesting challenge today.
So what's the, I mean, you focus a lot on interaction, right? Which makes a lot of sense, right? Like if we consider that technology and the evolution of technology is going to continue as we've seen in the past couple of years, things getting more powerful, smaller, and so on, reduced in form factor. What does that mean for the interaction? You know, do we have to sort of, how do we keep pace, right? How do we like align ourselves with sort of the disappearance of devices?
I think interactions will be more subtle and more passive, basically. I think a user won't focus so much on the specific interaction anymore. And I think developers and researchers will have to make it possible somehow.
I see. So a little bit going away from explicit input, more to observation and interpretation systems part.
Like away from standardized generic input devices like controllers or something.
The second thing, perhaps, I really like the analysis of the combination of modalities. That's, it's always magic that you find by connecting two things or more. What are some of the examples maybe for untapped potential that you would see for future work to explore more here?
Oh, that's a good question. I think there are some modalities which are really uncommon today. So we had a few modalities which we only found one occurrence of, like brain-computer interface and facial expressions. And I think that, so they have a lot of potential on their own, but I think also combined with our modalities, they can really do a lot of things. Let's see what the future thinks.
Thank you. We have a couple of audience questions now. The first one is, in the robot experiment, the only way to track the movements of the hand was the VR tool?
I don't know.
Okay, maybe we'll take this offline through Discord. The second one is a great talk. Did you also consider interaction techniques for handheld-based AR? So using phones in AR?
No, not in this paper, because we wanted to see what developers and researchers do if the hands basically are not occupied. So for a handheld, for mobile headsets and production-based AR, if there are any possibilities to do whatever you want to as a researcher and developer, because the user does not have to hold something in their hand. We wanted to explore what is possible then and what is used in this context currently. But we actually saw a few things about combining a mobile as a smartphone with head-mounted displays, which was really interesting, like a second device.
Awesome. Cool. Yeah, so that was the first talk. Thank you so much again, Julia and the team for this really nice structure over the work over the past 5 years. We're going to move on to the second talk now, which is HPUI, hand-proximate user interfaces for one-handed interactions on head-mounted displays, which is a collaboration between the University of Manitoba and Huawei, Canada. Sharif Falil is going to be presenting the paper next.
Yeah, thank you, Kristen, for the introduction, and that's a great talk, Julie. And I think my presentation will be kind of an extension of the discussion we just had. So I'm Sharif Falil, and I'm a PhD student at the University of Manitoba on the supervision of Professor Parang Irani. So I'm presenting our paper on HPUI, what we call hand-proximate user interface for one-handed interactions on head-mounted displays. By myself, Sharif Falil, Michael Cameron, Diane Huang, Kevin Fan, Bailey, and Parang Irani. So moving into the presentation, as Julia discussed in her presentation, head-mounted displays, or VR and AR, are kind of becoming next possible iteration for mobile computing and entertainment. Now, there are a lot of ways you would interact with these devices, and some of the most common interaction techniques, again, as discussed in the previous presentation, is like you have a head mount, like media interactions, or you have controllers. Now, one problem with these types of interactions is that they tend to be fatiguing. And also another problem is if you consider using these devices in the public, they are not necessarily socially acceptable, and also interacting with these devices in this way can be fatiguing. Like, you don't want to be standing in a coffee shop flailing your hand around, right? And and then you have the smartphones, like arguably the most common mobile computing platform we have. Inspired by the single-handed interactions that you see with smartphones, we are proposing hand-proximate user interfaces. The way we look at it is replacing, or the way we imagine is like replacing the physical device with a virtual interface. which could work with both augmented reality and virtual reality. And in our implementation, we are specifically demoing this in virtual reality. And we are particularly focused in single-handed interactions, single-handed thumb-to-finger interactions. And so a hand-proximate user interface is basically user elements or the UI elements that are displayed on and around the hand. And as someone asked in the previous presenters questions, like so one recent trend is like using smartphones as to augment the interaction of interactions with head-mounted displays. And what we are proposing is very similar to that. One advantage we have with HPUI is the fact that you're not carrying a physical device with you all the time. So you can easily transition between interacting with these menus on your HPUI and interacting with the work. And again, the idea of displaying UI elements on your hand and interacting with them is not new, but not many previous works have actually considered single-handed interactions while also displaying and interacting with elements. So that is kind of where our paper is positioned. And this is a simple demo of our HPUI. So here you have an interior design application where you place furniture. So traditionally, you'd have these very long menus that you would scroll through with, say, a controller or the hand. Here you have an HPUI which you can use to scroll through these long menus, which can ideally be a lot less fatiguing than using a control to scroll through them. And yeah, and say, for example, like you want to interface with your smartphone, that also could be done. Say, for example, you want to make a call, you can interface with your smartphone and interact with it in the same way you would interact with in a smartphone. And here you see the user selecting elements with their dominant hand using HPUI and placing it with their non-dominant hand. And they can just like iterate through this really fast because they're using both hands, right? And then you have the user selecting with the non-dominant hand and using the HPUI that is displayed on the dominant hand to reorient. And you see a map that is displayed on the HPUI, and the user can rapidly move around and repeat this task again and again. So that's a simple demonstration of what HPUI can do. And so first of all, we look at the design space of hand-proximate user interfaces, and we identify 5 different factors. The first one is the output space. And as I mentioned previously, we are particularly looking at single-handed thumb-to-finger interactions. So in that context, we can divide the output space into interactive space, output space, and non-interactive output space. And when you consider the interactive or the input part of the output space, this space, you can further divide them into on fingers, that is places on or around the hand where you can actually have tactile feedback, and then off fingers. And then you have where you'd be displaying these elements. So you have around the hand, between the fingers, on the palm, on the finger, and above the finger. And then given the fact that when you're doing specifically when you're doing single-handed interactions, your hand deforms a lot. Your hand is moving and deforming a lot. And considering the anatomy of the hand, we also have to consider where a displayed element is going to be anchored. So the X marks that you see on these images are some of the places where these elements can be anchored. And so we are looking at, generally, we are categorizing them into palm, individual phalanx, whole fingers, or multiple fingers. And then again, considering the dexterity and how the hand deforms, you can divide the workspace into 2 as well. So like you say consider the home screen of a mobile phone. So this has elements that can be broken into individual UI components. So we consider that as a discrete workspace. And then you have workspace which have elements which cannot be broken down to discrete elements. Think maps or images. So that would be the continuous. So consequently, we run 2 studies. And in the first study, we compare direct as afforded by HPUI to indirect input. And then we explore how someone would interact using HPUI on a continuous deformable surface. So we run our studies using the YCOM platform for accurate hand tracking and the Oculus headset to display and interact with virtual elements. So in the first study, we are comparing direct with indirect. We have 2 different input modes. The direct input mode actually has the target elements being displayed on the hand model that is mapped to the motions of the user's hand. So the task, the task we had for the first study is a target selection task where we compare the completion times. And the indirect input mode has the target elements being displayed in a static hand that moves with the user's head, and the user would select the targets with indirect thumb to finger interactions. We also consider the target locations on the hand, on finger and off finger. Overall, we observe that interacting with targets that are directly placed on the hand performs much faster. And also, we ask the participants to rate the different target locations, similar to some of the previous works that have looked at the functional workspace of hand. And the findings, the ratings that we observe are very similar to what we've seen in previous studies. And for the next study, we look at continuous interaction, the continuous interface. Now, these are interfaces, as I described before, that cannot be broken down into individual discrete elements like a map or an image. And we are considering what we refer to as the deformable interface. So this is an interface that moves with the as you move the fingers. An advantage of the deformable user interface is one, it allows you to reach more regions compared to a planar surface, and it also has the advantage of providing better potential for tactile feedback. So for the second study, you have two different tasks. First is a target selection task, and the second is a dragging task. Another thing that we did was so from the previous study, we observed that the region around the pinky finger is not the most comfortable to interact. As a matter of fact, we had to exclude one participant because he couldn't interact with the pinky finger. So in the second study, we also wanted to see if the space above the index finger, that is the space between the index finger and the thumb finger, if that also can be used to display and interact with elements. So overall, what we observe is that the regions or motions that are closer to the thumb perform much faster. And in the second study also, we were comparing completion times. So in conclusion, inspired by the results that we see, we implement a set of simple demos on the Oculus headset using the Oculus's hand tracking. So the clips that you see on this slide are basically just using the Oculus's hand tracking. And what we see, these are simple demonstrations that show the utility or the advantages of using an HPUI. So that is basically providing users with an interface that is very similar to using how they would interact with a smartphone, which can be used in both virtual reality and potentially augmented reality as well. And thank you. That's the end of my presentation.
Awesome. Thank you very much. So I noticed that people are starting to use the Discord channel, so please keep doing that and post the questions in the respective channels or here on Zoom. Maybe I'll kick it off again, unless there are any. Yep. Okay. Thanks, Shara, for the great talk. Also super cool because I think this is quite enabling for sort of in situ situations going forward where we might be able to make use of these mixed reality interfaces for interacting with contact or executing productivity tasks even. And I think your interaction technique is really promising because it's a quick alternative to the direct interaction in midair that we're seeing a lot these days. And I noticed that in your examples, the hand was always within the view, the field of view of the user to guide the input and to select from a set of options. I think there's a potential here to extend this to eyes-free operation where you're working with or on the content while controlling it from a comfortable area. So is this something that you've thought about too?
Yeah, that is something that we plan on looking at in future works. Yeah, so that is definitely one factor that we want to actually consider. So since we are using the hand tracking of, say, the Oculus headset, yeah, one problem is the hand always has to be in the FOV, which is not always ideal. So that you have to actually be looking down at the, say, if you're using, for example, the HoloLens, you have to actually be looking at the hand, which is not very comfortable. So we are looking at different ways of interacting indirectly as well. Yeah.
Yeah, there's also the potential to basically learn that, right? I noticed that you had the imaginary phone in there. right? Where we talked about the aspect of transfer learning, right? Where people like repeat these tasks over and over. And given that you give them additional visual guidance for the task, right? This is a really great idea. Also connected to the previous talk, as you mentioned, for more subtle interaction, right? To interact with like the grand space in front of you in mixed reality scenarios. We have a question here from Mark. How would your system compare to a real smartphone? Do you plan to compare this in the future?
Yes, like in the future at some point, yes. Like right now, what we realized is there are a lot of smaller problems that we have to solve, and most of them around the fact that you have a very deforming, like a very say dynamic surface, right? The hand is not as static as the smartphone, so directly comparing them is not possible. So that is one thing that we realized early on. So yeah, like after a few iterations, at some point, maybe yes. Does that make sense?
Yeah, yeah. Maybe as a follow-up and somewhat related to the first question, HPUI also seems like a nice solution for tests that are a bit longer in execution, where you have to spend more time on them. And then, of course, the hand in the field of view. I mean, you touched on this a bit. It can become heavy. I mean, this is probably not something that you considered so far in the design of the techniques, right? But I also remember Parang's paper from a couple of years ago where he investigated the fatigue incurred by execution things, such tasks, right? Is this also something that you're factoring in maybe in another iteration on the technique?
Yeah, so like bringing your hand closer to the body. So that is that was the inspiration for using smartphones. Like people use smartphones like all day, all the time. So that is so we are kind of building on the smartphone interactions. And yeah, like because of the FOV limitations, your hand has to be a little further up. So yeah, in the future iteration, we would like to have the hand more closer to you, so that it's more comfortable.
We have a question from Joseph here. I see you use a glove that recognizes the hand. Do you think that it's possible to do the same thing, recognizing the hand with a hand recognition algorithm?
Actually, yeah. So like, so the glove was actually used for the studies. Like, so we didn't like the problem with the hand tracking algorithm. They are not very precise as it is right now. And like, even if you take, for example, the MRTK, even they recommend against using hand tracking for like placing elements on your fingers and stuff like that, because the hand tracking is not accurate. So that is why we used the Vicon system to run the studies. But the demos that you actually saw were based on the hand tracking on Oculus. So yeah, like if you have a fairly, even with its like the problems that it already has, it seems to work okay for now. And so with the so we had another session in the morning which looks at like hand tracking. So the hand pulse estimation and hand tracking is moving at a really fast pace. So I'm assuming very soon we'll be able to have accurate hand tracking, which could be used for more reliably for HPUI as well. Very
cool. Also a great opportunity to bring this out and about, right? And take with you where you go to make use of this. Very cool. Yep, thank you very much. Yeah, I think we should keep it at that. And let's thank Sharif again for the great presentation of his work and the work of his team. Next up, we have the paper Rotational Constrained Optical See-Through Headset Calibration with Bare Hand Alignment. And it's going to be presented by Xu from Imperial College London. Take it away.
Okay, I'm going to share my screen. Okay. Yeah. Okay, thanks for the introduction. Today, I'm happy to present the rotation-constrained optical see-through headset calibration with bare hand alignment. This work is collaborated between Imperial College London and University of Pisa. Here is a warm greeting from all the authors. So our method uses a commercial RGBD camera to marketlessly track the user's bare hand and exploits the tracked dense point cloud to calibrate the OSD AR headset in a user-centric way. Our method is efficient, robust, and implementable in commercial AR headsets. In this paper, we use Microsoft HoloLens 1 as an example. The OST HMD has been proved useful for surgical tasks by projecting the virtual guidance in front of surgeons' eyes and reserving their natural view to the patient. The surgical intervention can be completed in an immersive and safe way. To ensure the accuracy, the projected AR content should be locationally consistent with patient anatomy under surgeon's perspective. This leads to the topic of OSD calibration, which aims to correct the AR headset's rendering pipeline according to users' perception. While the first-person observation is not recordable, we need to solve the eye-seeing projection. State-of-the-art OSD calibration methods can be divided into two categories. The alignment-free method uses calibrated eye tracker to track users' eyeball. They require no user involvement, but dependent on dedicated hardware and complicated extrinsic calibration. Furthermore, the eye trackers track the center of the eyeball instead of the actual nodal point, which compromises calibration accuracy. By contrast, the alignment-based methods require users to collect virtual-to-real correspondences by manual alignment, from which the authentic viewpoint-related information can be decoded for projection correction. Despite the user involvement, they are more implementable for commercial AR headsets due to their lower dependency on hardware. Therefore, in this work, we focus on the alignment-based methods. Current alignment-based methods usually require users to align one or a few landmarks on a calibration tool to the displayed virtual cursors. Such alignment scheme has several limitations. First, special calibration tools with artificial landmarks are usually required, which makes it impossible to calibrate anytime and anywhere. Second, the required manual alignment is usually pointwise to pre-designed cursor locations. Users may need to move a lot for the alignment. Third, only one or a few correspondences can be collected per alignment. Thus, repeated alignment is required to collect enough correspondences, which increases users' workload. And finally, the calibration accuracy is heavily dependent on the user-performed alignment. Poor alignment by unexperienced user leads to poor calibration accuracy. To solve these problems, we propose a user-centric calibration scheme that directly exploits users' bare hand. The required alignment is object-wise to a hand cursor generated in a user-specific way. Each alignment will provide thousands of unpaired correspondences so that single alignment can potentially ensure reliable calibration. Finally, our methods can constrain the rotational misalignment performed by unexperienced users. Let's start from an overview. Our prototype system consists of a commercial AR headset with an anchored RGBD camera. At the frame TA, the user presents his or her hand to the system. The 3D hand points will be automatically segmented from the depth camera recording and sent to AR headsets. To generate a customized hand contour, since the OSD display is not calibrated, the user will notice a misalignment between the cursor and the physical hand as shown on the screen. He or she should translate their hand for proper alignment. Once the alignment is confirmed at the frame TB, the new 3D hand points will be segmented. The two-point cloud are used to optimize the eye-related parameters for projection correction. Next, we will explain the details of each step. Our method is based on a homographic corrected off-axis eye display model in the literature. Assuming an on-axis camera display system ES, the eye display projection can be expressed using equation 1, where on-EK is hardware-determined on-axis projection intrinsic, H is a homography-related matrix, and E is an extrinsic related matrix. Starting from an offline calibration at arbitrary viewpoint, the new correct projection relation can be expressed using equation 2, where we let H1 equals to H0 times U, E1 equals to Q times E0. The multiplication of UQ can be written as equation 3, where phi 1 to 3 are 3D distance between old and new viewpoint in the eye display system, and phi 4 is an original eye display depth that can be calibrated offline. So overall, the goal is to find phi 1 to phi 3 so that the off-axis head projection P can be corrected using the expression in equation 4. For the markerless RGBD hand tracking, we train a MovaNet V1-based SSD network on the Oxford hand dataset to locate the region of interest for the hand in the captured RGB frames. The aligned depth frames were cropped by the predicted ROI and filtered by the depth camera working threshold, resulting in the tracked 3D hand points. We allow the user to generate customized cursor with their own hand at self-dedicated locations. To this aim, the cropped depth frames were converted to binary masks and processed to generate contour mask, which is displayed as the reference cursor by the headset. Then finally, our goal is to find phi 1 to phi 3. At the cursor generation frame TA and alignment frame TB, we have equation 1. Since the hand movement in depth is negligible compared to headset's focal distance, we can write the equation 2. The task can thus be converted to a registration problem, but with the transformation matrix M in a unique expression, which is only determined by phi 1 to phi 3 only. Since the correspondence is unknown, we developed an optimization method with iterative closest point searching to minimize the point-to-point registration error. In fact, since the multiplication between phi 1 to phi 3 and phi 4 is very small, the rotational part of M is nearly identity. So that means the perfect hand alignment will expect little relative rotation during the hand movement. We thus call the method rotational constraint ICP, or RC-ICP in short. So here shows the registration result between two hands. We run a simulation test to show the robustness of our RC-ICP. With up to 9-degree misalignment, the inaccuracy is estimated in the estimated phi 1 to phi 3 is less than 4 millimeters threshold chosen from the literature. We thus designed the UI interface based on this observation. So on the right, you can see when the relative rotation is larger than 9 degrees during the user alignment, the tracked hand surface will change color for warning. This is the pairwise recording from the RGBD camera for hand tracking and eye replacement camera for the AR overlaid scene recording. For the evaluation part, we first evaluate the calibration accuracy by placing an eye replacement camera in the headset's eye box. This allows us to objectively record the scene that what is an actual user can observe when the OSD display is on. An Uruko marker cube is used as AR target. We did the pairwise capture with the AR display on and off. The Uruko cube poses were detected individually from each frame. The difference between the two poses was recorded as the calibration error shown in the table. So with a single alignment, our method can achieve 1.37 millimeter 2D positional error and 1.76 rotational error. Then we involve 3 users to evaluate the reprojection error. After each user performed calibration, users are asked to manually adjust the cursor location to align to the center of a Uruko marker. The cursor location is locked as ground truth pixel locations. We evaluate the reprojection error at the 4 Uruko corners indicated by the red cursors. We can achieve 10.79 arc mean or 7.71 pixel reprojection error, which is better than the state-of-the-art finger-based calibrations. That's the end of my presentation. Questions are welcomed.
All right, thank you, Shu and collaborators. As always, questions please on Discord or here in the chat. I'll start off with the first one. And I have to say, that was a really timely topic. And I think everyone who's used these systems in the headset understands the challenge that you set out to address here. And sometimes it can even be a bit confusing when you use it and there's an offset between the hand and where the system models it. I think you presented a great technical solution to this. And I'm wondering if you've investigated some of the questions that also relate to the user's perception, perhaps. Do we have any sense of the impact of the problem for using a UI system?
For the calibration accuracy, you mean?
Mm-hmm.
Yes, probably that's one of the research direction. Actually, when we designed the UI interface for the hand alignment, we did care about this problem. So initially, we display all the tracked hand points on the screen directly, but we realized like when we ask the user to do the alignment, they cannot focus on the contour or the perfect alignment because you basically have a 3D object in front of you and you have to align another surface with that. So finally, we decided to convert that 3D raw hand points to the contour so that they can use a kind of the shotgun game to decide for the overlay of the hand contour and the perceived contour. For the current implementation, because probably I mentioned in the related work, so far all these works require you to do multi-point alignment. So for example, you have a 3D Uruku cube and you have like 3 or 4 not in plan corners displayed to you, and you have to simultaneously align those corners with the actual 3D cube. But this requires a very heavy mental load. And also, although the alignment quality, alignment task is quite easy because it's point to point, but you have to simultaneously decide the multiple point alignment. So it's not a very mental easily work. But like if there are any like interesting or any advanced display technique, we are happy to listen to these suggestions in the future.
I see. Yeah, that makes sense. Are you thinking a little bit about how to alleviate some of these things and make it less complex for the users going forward? Perhaps this is something you're working on right now and it's already in submission. But
yeah, from our own experience, we can say display a cursor, then align to it is the current standard. And also because it doesn't require too much complicated understanding, so it's quite intuitive and straightforward. More UI interface probably means clearer instructions for users to for each step, but not like probably not for the alignment step.
It's a really interesting question, given you mentioned it's intuitive and seeing the cursor. I think this is something that technology has sort of almost conditioned us to find intuitive, right? Like because basically, if you really think about it, you sort of convey to the system how you want to use it. It tells you what it understands, and then you correct based on what it displays that it thinks what you did, right? Which is sort of not like sort of as intuitive as it should be, that you just do something, right? So I think it would be really interesting to also get a sense of how people perceive this, right? And then maybe run this on a couple of people, try this out and see what is the impact that this difference and with this technology that you built to improve this and solve this problem, how this makes things better, right? From a user's perspective, especially with regard to maybe
that's also one of the motivation why we invent this system, because those previous methods usually like use pre-designed cursor locations. So that means for a user, from their perspective, they cannot know what's the pre-designed location, but they have to control everything by themselves to navigate to those cursor locations. And this probably means a lot of space or the uncomfortable alignment gestures, which incurs a lot of instability during the alignment. So that's why we use the relative transformation from a first generated cursor location to an updated one. So because the display misalignment can never be very, very big. Otherwise, the display cannot display anything in the field of view. So in this case, the correction probably means a relatively small translation for the hand. So they don't need to hold the hand for a long time and also in a very uncomfortable distance and gestures, and also use their own hands so they can make any gestures according to their willing.
That was a very nice wrap up. Thank you very much. Thanks, Xu, again, and team. We're going to move on now. The next paper is a collaboration between ETH Zurich, the University of Cambridge, and Saarland University, and the title is Complex Interaction as Emergent Behavior, Simulating Mid-Air Text Entry Using Reinforcement Learning. And Lawrence will present it now.
Sorry, I seem to be having a few microphone issues. I'll just switch over to my headset. All right, I hope you can hear me now.
Yeah, it works.
Excellent. Thanks for the introduction, Christian. Welcome to my presentation. The title is a bit of a mouthful of complex interaction as emergent behavior, simulating mid-air virtual keyboard typing using reinforcement learning. And as Christian already said, it's a collaboration between ETH Zurich and Cambridge. And if I'm a little slow today, apologies. I have a bit of a fever, so I might go a little bit over time. We'll see. All right, let's dive right in and have a look at the problem we are tackling in this paper. As virtual and augmented reality become more prevalent, we're going to have to deal with text entry in these environments. And as many of you will know, this is still very much an unsolved problem. I'm sure there are many great papers being presented on this very topic at this conference. But one thing that all of these novel approaches tend to have in common is that they need predictive techniques that isolate users' intent from noisy movements that can occur in 3D space. So the development of these systems, as with most HCI systems, requires a lot of human testing. First, you need to find a good design with preliminary testing by trying out things yourself, or maybe asking for feedback from some of your colleagues. And then you would usually conduct a user study to finally evaluate the performance of your system. And the whole idea behind this paper was to replace some of the human input during the testing of these very explorative input methods with a user model. Of course, the idea of having a user model is about as old as HCI itself, but existing models are often highly specific to a particular interaction task, and most importantly, which limits their applicability to, it seems to be progressing on its own. These models, what limits their applicability to novel input methods is that they require user data to be trained or to be calibrated. So what we are looking at is a system that does not rely on any pre-existing user data and instead relies on reinforcement learning. So from this problem formulation, we isolate two very specific research questions. The first one is it even generally possible to learn a complex interaction task such as typing using the current reinforcement learning techniques? And then secondly, should we succeed, does the resulting model exhibit human-like characteristics? And almost more importantly, can we actually use it to generate some useful data to pre-train other typing-related algorithms? Such as key hit detection, for example. Let's take a step back for a moment and have a look at some related work. The work on the left looked at something quite similar to what we're doing. They predict fatigue in mid-air interactions using a biomechanical model and reinforcement learning. However, they consider only very simple targeted reaching movements. And there are other papers like this. And they often use highly simplified arm models, which also limits their realism. And on the right, we have a paper that's not exactly directly related, but it just shows how dexterous of a task can potentially be learned with modern reinforcement learning techniques. In this particular paper from OpenAI, they trained a hand to rotate objects into a certain target orientation without dropping them. And yeah, let's look at the first building block for our model, which is the underlying arm model. Surprisingly, at least to me, there are very few biomechanically accurate models of the human arm. There is this one, which we are using, which was developed for the Stanford Open Simulator. But for example, there is no model available for a female. This model approximates the average American male. And Stanford Open Simulator, some of you may be familiar with it, is a very powerful simulation suite for biomechanical models. It's very accurate, and it's the gold standard in the industry, really. But the problem is that it's also very slow and not very well supported. So we actually use a version of the model that was converted to the Muzhakov physics simulator, which is very fast and commonly used in reinforcement learning. And lastly, the original model has 50 muscle compartments. So essentially, at least come from a mechanical engineering background, basically linear actuators, which make the control problem basically impossible to solve using reinforcement learning. So we follow another common approach for reinforcement learning of biomechanical models, which is that we remove the muscles and replace them with 7 direct torque actuators at each of the joints of the arm. And then to approximate the muscle behavior, you then add what's called a muscle model that mimics the torque response of I know what this is, that mimics the torque response of muscle-driven joints more. Yes, sorry, the progression is from my narrations that I recorded for the video. Yeah, so for time reasons, we won't be really getting into the specifics of this, but the reinforcement learning problem is described in more detail in the paper, but just for completeness, we use soft actor critic, which has recently been applied with great success to a number of challenging mechanical control tasks. Now that we actually have a model, how do we actually train it? The most naive approach would be to just give a reward if the correct key is hit. Unfortunately, we found that this doesn't converge. So what we have ended up with is a 2-stage training regime. At first, we train with a position-based reward. That means the reward is given as long as the target key is reached within a certain time limit, even if other keys are hit along the way. And then once that converges, we switch over to a hit-based reward where we actually only give the positive reward if the correct key is pressed. And if any other key is hit along the way, the model gets a negative reward. And before we have a look at the trained model, I would just like to reiterate 2 things. This model was not trained using any user data. The observed behavior arises fully from a simple cost function that minimizes movement time. And also note that posture comfort and fatigue are currently not explicitly modeled. That's something we've left for future work. Yeah, so here's our model typing away. But as you'll notice, it's only one arm. That is because the upper extremity model that we're using only contains a right arm. But since typing is very much, at least for most people, a 2-handed or bimanual process, we came up with a little trick to simulate bimanual typing with 2 right arms. We basically take 2 right arms, but let one of them type on a flipped keyboard, which is equivalent to flipping the arm, which turns a right arm into a left arm. And then we interleave their movements. Once again, more details on this process can be found in the paper. We then evaluate our model on a benchmark user study conducted by my co-author John Dudley about 2 years ago. They had 24 participants and had a very detailed motion capture data for both mid-air and surface aligned typing, which made it perfect for our application. Let's look at the actual alignment with user behavior. On the left, we have a box plot of words per minute. And as you can see, our model is quite well aligned with what we observe in the user study. That is to say that users tend to be slightly faster in surface aligned typing. This alignment is quite surprising if you don't think about it too much, because as I said, this model was never explicitly trained to approximate human behavior. So in a number of simple metrics, such as words per minute and character error rate, our model is quite well aligned with human behavior. And most importantly, it is competitive in terms of typing speed and accuracy with humans. But, and this is inevitable for any honest evaluation of a user model, there are some shortcomings. So for example, on the right, we have a character error rate box plot, and our model predicts that character error rate will be lower in surface aligned typing, but that is not what we actually observe with real users. So the real question we would like to ask in our evaluation is not, does our model imitate human behavior perfectly? It can't, because it isn't explicitly trained to do so, but rather, does it correlate, so to speak, with humans well enough to be useful? So the concrete application we're going to be looking at is hyperparameter selection. So let's say you were developing a new keyboard for virtual reality and you wanted to optimize the character error rate in your user studies. Optimizing the underlying parameters that affect character error rate numerically is very time consuming. So the question we're asking is, can we use our model to select hyperparameters in an objective and reproducible way? We're going to evaluate this against two benchmarks. The first is usually most parameters of an HCI system are never numerically optimized during development. For example, if you're busy developing a novel interface and you're not going to spend the time to optimize the size of each button in your interface, usually you would just sort of randomly pick it. So to start out, we are just going to look at if our model can outperform randomly choosing hyperparameters. And secondly, let's say you have an important parameter and you're really willing to spend a lot of time generating training data. In our specific case, in the user study, we would have been talking about roughly 4 hours of typing stimulus phrases. But even if you put in that time, at the end of the day, you're only one person. So the question is, can our model even be more indicative of the general population than some users might be? As I said, the first scenario we're looking at is what is the probability that the model may choose better hyperparameters than a random set of hyperparameters? So if you just randomly pick one. And the answer is 99.8%. So in almost every case, our model will outperform randomly guessing a hyperparameter. And in the second scenario, we would like to see if our model can even choose better hyperparameters than some users can. And the best we could really hope for here is about 50%. That would mean our model is exactly the average user. And we don't quite reach that number yet, but given the context, I would argue that 38% is already pretty good. That means that if you put in the 4 hours of effort it would take you to run this sort of optimization on yourself, you have a 38% chance of still being outperformed by our model, which would have cost you 3 minutes to set up, and then you just let it run while you go get lunch. The fact that we are so close to human performance is particularly impressive if you remember from the last slide how poor random sampling performed. So while these initial results are quite promising, there's still quite a bit of future work left to be done. The first major limitation is that our model is currently symmetric. So the first task would be to create a biomechanical model of the left arm and train an agent that can control both arms at the same time, which would be a challenge in and of itself, but should be feasible. And secondly, the model exhibits relatively low variance when compared to a crowd of real users. So if you recall the words per minute and character error rate box plots, the solution here would be that we could add domain randomization, which is very commonly done in reinforcement learning, and actually leave it turned on at inference time. So for example, we could parameterize the bone length of the underlying biomechanical model and such things. And lastly, our model is currently only typing with 2 fingers. From our initial impressions, it would seem unlikely that real 10-finger typing can be learned using just current reinforcement learning techniques. We would expect that you would need to use demonstrations or imitation learning to warm start the reinforcement learning algorithm. So to summarize, we've shown that the novel reinforcement learning approaches that have been released in the last couple of years really enable us to develop a whole new category of user models. These models do not rely on any pre-existing user data, which makes them perfect for applications such as the one that Sue presented just before me, where it's a very novel approach, so you don't really have much existing user data. And lastly, we showed that very complex interaction can emerge from simple cost functions, which is kind of fascinating to me. And yeah, thank you very much for listening. And if you have any questions, I'd be happy to answer them.
Very cool. Thank you so much for this presentation. Very nice work. I really like the approach and the method of bringing computational methods to this problem, right? And trying to like skirt perhaps some of around some of the issues that go along with text entry methods, where you involve a lot of users, and finding alternatives to this is definitely appreciated by a lot of us, I would assume. I don't see any questions so far. I'm just going to ask one, and I actually want to. I found it very intriguing. I want to challenge this a little bit. I mean, you did this for like mid-air text entry, right? Which is very reasonable, makes a lot of sense. I really like what you demonstrated. I was wondering to what extent you think this would translate or maybe generalize to text input anywhere, perhaps even on surfaces, which is sort of the task that we're used to, right? And that you're doing right now, right? Sitting in front of a computer.
So I perhaps wasn't too clear on this in the presentation because I was going through it quite quickly, but the model is capable of both surface aligned typing and mid-air typing. Sorry, that was unclear. It's two different models, but they're trained in the exact same way and using the exact same hyperparameters. But it's basically, in the surface aligned case, we are simulating like a projected keyboard, or basically touchscreen typing, right? If you're talking about like a mechanical keyboard, I think it would be a bit more challenging because you have like rigid body interactions that the model would have to cope with.
Right. Yeah, no, I think just alone for the touchscreen, as you say, touchscreen typing or projected keyboard on the surface, that makes a lot of sense. You shouldn't add new constraints and in terms of the support that you might have for the body itself, for the arms and so on, right? Which confines the motion a little bit, but then also supports it. And that becomes really interesting, as we heard in like previous talks, with regard to fatigue and prolonged interaction in situ.
Yeah, that is actually something that we could definitely look at for future work, adding a muscle model that would allow us to predict fatigue. It's not something that we covered in this work yet.
Yeah, if you're still at ETH, just swing by. We have a lot of work going on in this area.
Yeah.
So we have a comment from Sheriff. This is such a cool approach. Awesome presentation. Would it be possible to model human biases as well, particularly with novel interaction techniques? For example, on flat surfaces, prior work has shown users rest less on the touch surface when not performing a keystroke, which probably because of prior experience with touch surfaces.
So like explicitly adding that to a model would not work. And I think that would also kind of go against the whole logic of this. But to be honest, in this case of a touch surface, I would, so basically you're thinking like if I have, I'm just going to extrapolate a bit from the question. If you have a novel system that does perfect palm rejection, users will still not rest their palms because historically they've been used to systems that do not have good palm rejection. In incorporating something like that is actually one of the shortcomings of an approach like this, is that we don't have any fine-grained control over the model. So we could like explicitly add a cost function, basically simulate as if our input device didn't have good palm rejection, but that would sort of be going against the whole idea of this approach.
It's I mean, your answer makes perfect sense, but it's a really good question actually, because it reflects on some of the learned behavior of people in response to how technology is or had traditionally been implemented, right? Which is not necessarily the point from which you start at. So that there is a bit of like influence on people that then change the behavior to accommodate to how we implement technology that you would have to, in order to like make it perfect, quote unquote, right, also account for in the method.
Yeah, so you could definitely do, I mean, it's really fascinating. So it's also one of the first bigger works I've done with reinforcement learning, and it really is a little bit like a cat. So if you wanted to simulate this sort of behavior, you could really think about basically pre-training it on an iPad that doesn't have good palm rejection, so to speak. And then letting it type on one that does have good palm rejection. And you would probably see something quite similar to this, but that's not the most scientific thing I've said today. It's more of a gut feeling.
No, I think that's fine. All right, I think we're out of time with this one. Thank you so much again, Lawrence, and collaborators for this talk. And with that, we're going to move on to the final talk in the session. It's on a predictive performance model for immersive interactions in mixed reality. And Florent Cabric is going to present this paper.
Okay, I think everyone could see my screen now.
Yes.
Okay, so hello everyone, and thank you to be here just before the break. Today I will present my work, a predictive performance model for immersive interactions in mixed reality. So my name is Florent Cabric. I'm a PhD student until October 13th. And this work was made in collaboration with Emmanuel Dubois and Marcos Serrano, my PhD supervisors. The last years, a lot of work with head-mounted displays evaluate applications, interaction techniques, or systems with users. But testing and evaluating this kind of system requires considerable time and effort, especially with the COVID-19 pandemic that prevents researchers doing controlled experiments. To overcome these issues, predictive models can be used to predict the time required to complete an interactive task at an early stage of a design process. So in this work, we propose an extension of a well-known model, the keystroke level model, or KLM. The keystroke level model is part of a GUMS family. This model can predict the time to complete an interactive task. This task consists in a sequence of atomic actions. These atomic actions are called operators in KLM. Each of these operators are associated to one or more units time. The KLM original was designed to predict completion time for interactive tasks in a command line systems, but these systems are now outdated. We need to adapt the model, the KLM model, to new technologies. This kind of extensions already exist for mobile phones, in-vehicle systems, or smartphones. But as far as we know, no KLM extensions exist for interaction for mixed reality application. In this work and this presentation, we propose a KLM extension for mixed reality. We focused only this work on selection task as a sequence of a pointing action and a validation action. During this presentation, we will fill in the table at the top of this slide. The first operator models the cognitive actions. In interactive system, many actions require a reaction time to start a new action, for example, after feedback. The simple reaction operator was designed by McKenzie in 2013 to model this kind of reaction. In a mixed reality HMD environment, the digital field of view is reduced compared to the human eyes, the field of view of human eyes. So most of the digital content with HMD is placed outside the field of view. Thus, exploring the digital space requires wide head movements. These movements are modeled with a coarse head point operator. Once the content is displayed inside the field of view of the HMD, to select one item, the user needs to point at this item with a cursor. In most of HMD now, the cursor is placed in the center of a field of view. This action requires slight head movement to move the cursor from a target to another one. These movements are modeled in a KLM with a precise head point operator. Once the cursor is on the target, a validation step is required to select it. This validation step can be done either with a dedicated device or with a mid-air gesture. Usually, the HMDs are delivered with a dedicated device with a physical button to validate a pointing or to select a command. The action to click on a button on a physical device is modeled by the button click operator in our KLM. As I said, we can also perform a mid-air gesture to validate a pointing task. the HMDs now can recognize a gesture with the arm or with the hand. But to detect these gestures, hand must be detected in the field of view of the HMD. So the user has to move their arm from a resting position to a position detected by the HMD. The raise hand operator models this action, this gesture. And the last operator, once the hand is detected by the HMD, as I said, a gesture to validate can be performed by the user. Each constructors of HMDs create a specific gesture to do mid-air validation. In our work, we choose the AirTap gesture from HoloLens because the gesture is easy to perform and robust. Indeed, this gesture is present in HoloLens version 1, also in HoloLens version 2. To sum up our new operators, we have 5 newly introduced, 2 for pointing a target with a coarse head point and a precise head point operators, and 3 to validate a pointing, the button click, the raise hand, and the AirTap operators. So we now have our 6 operators to model the selection task in a mixed reality HMD environment. But an extension of KLM requires to define a unit time associated to each operator. To this end, we designed 4 user studies with the HoloLens, HoloLens version 1, and each study was conducted by 12 participants. For the first operator, the coarse head point operator, we need to model the time taken by users to bring the field of view of a HMD around the target. However, the vertical field of view is smaller than the horizontal one. To avoid and overcome this problem, instead of bringing the field of view of the HMD around the target, the user has to bring a circle inscribed on the field of view around the target. The circle inscribed in the field of view is represented in blue on the picture. So in this study, we placed 8 targets at the 8 cardinal points and at 3 different angular distances, 45, 60, or 75 degrees. In this study, the user has to 1, look at a 3-second countdown, 2, bring the circle inscribed in the field of view around the target, and 3, stay 500 milliseconds to validate it. We collected 576 movements. We can see on the graph that the direction of the movement has an effect on the completion time. And we can also see that the angular distance has an effect on the completion time. So we cannot only define 1 unit time for this operator. We decided to define 9 units time for the 3 distances and the 3 directions in this operator. For the precise head point operator, we set up 8 targets on the inscribed circle. The participants have to 1, look at a 3-second countdown, 2, bring the cursor to the target, and 3, stay 500 milliseconds to validate the pointing. Unlike the previous operator, we do not observe a clear difference between the directions. So we define only 1 unit time for this operator, 490 milliseconds. At this time, we define the units time for the 2 pointing operators. We define 9 values for the coarse head point and 1 value for the precise head point. I will now present the studies for the last 3 validation operators, the button click, the raise hand, and the AirTap. For the button click operator, the participants must look at a 3-second countdown and perform 4 button clicks. For the raise hand and the AirTap operators, the participant must also, always look at a 3-second countdown, raise their hand in the field of view, and perform 4 AirTaps. The button click takes 207 milliseconds in average. The raise hand takes 623 milliseconds in average, and the AirTaps takes 427 milliseconds in average. And now we have an extension of KLM complete, but it's not sufficient to have a proper KLM extensions. We need to consolidate our model with a sequence of operator, a task more ecological. So in the next slide, I will present different consolidation studies to validate the ability of our model to predict interaction time. we ran 3 consolidation studies and we compared the time predicted by our model to the mean time observed during our experiment. According to Olson and Olson in 1990, the difference must be less than 20% for each task to validate our model. The 3 studies represent common tasks in HMD mixed reality. We have 1, pointing targets outside the field of view. The second task, selecting multiple targets outside the field of view. And the third task, and the last, selecting multiple targets inside the field of view. These 3 studies are necessary because they involve different sequences of operators. For the first task, the first study involves a simple reaction, the precise 8-point and the coarse 8-point operator. The task is for fun, 2, bring the field of view around the target, 3, move the cursor to the target, and 4, stay 500 milliseconds to validate it. For this task, the differences between the predicted and the mean observed time range from 0% to 10%. So this task validates our model. The second study is a 5-target selection task where targets are placed outside the field of view. This task involves a coarse 8-point operator, a precise 8-point operator, and a button click operator. They have to bring the field of view around the target, point at the target in 2, and 3, validate the pointing. The difference for this task is only 1, so this also data model. And for the third and the last task is always a 5-target selection task, but in this study, the targets are placed inside the field of view. So after a countdown, the user has to 1, point at the target, the precise 8-point operator, 2, only for the first target, raise its arm, and 3, validate the pointing with the R tap. For this task, the difference is 4.8%. So the 3 tasks validate our model. To sum up all of the contribution of this work, we propose a new extension of KLM for mixed reality. First, we design new operators. Second, we associate unit time for these operators, and then we validate our model with 3 user studies, 3 validation studies. In the near future, this model can be extended from different perspectives. First, mixed reality devices allow the user to carry out other forms of interactions. For instance, after selecting a 3D virtual object, the users can perform 3D manipulation. Modeling these interactions requires additional KLM operators, and we need after to define unit time for these new operators. And finally, and we also see during this day and this last presentations, combining touchscreens with HMDs could be useful to overcome mixed reality mid-air interaction problem. So to this end, it will also be interesting to extend our KLM model with operators for smartphone-based interaction. So thank you for listening. And if you have any question here on Gavertan next, I will be happy to answer them. Thank you.
Thank you very much, Florent. Questions in Discord or here in the chat for now? Maybe I'll start again. It was very nice to see the interactions in the AR interface formalized a bit more and used for UI evaluation. So that was really refreshing, I would say. In your case, you picked the interaction vocabulary of the HoloLens 1, which made a lot of sense, right? And they used a combination of head gaze and activation through tap or click. And you touched on this in your future work a bit, but what are the challenges that you see in extending your model to where the interaction design is currently going, as we heard in the previous talks, right? So cursors guided by hands, as we heard earlier, remote interaction through indirect input, or even direct interaction with the UI in front of you.
Yeah, so for the first part of the question, yes, we use the HoloLens version 1 because we think it's one of the most common HMD. Yeah. And the vocabulary of interaction with HoloLens version 1 is robust, but we can think a little bit later, especially with HoloLens version 2 and the eye gaze and the eye tracking inside. But just to explain, we all of these are operators with HoloLens version 1 are still validated in HoloLens version 2, and we think about it when you design it. For instance, when you develop all the searching and pointing tasks, we express the fact that we have a circle inscribed just to overcome these issues of different HMV field of view and size of the field of view of different HMV. And if you can think about the next model and the next operators, we have plenty of gestures that we can imagine with the body, and especially with fingers. And we think about all the gestures with each finger can be really, really interesting to investigate. And I think, yes, it could be a great work, but we have no time to take this work just for selection tasks. I think I answered your question. Maybe not.
Yeah, no, that's good. And then perhaps one detail I picked up on at the beginning, you mentioned your PhD is over next week, like you want to use this platform for outreach.
Yes. Yes, I said it on the Discord. I'm looking for a postdoc for 2022. If anyone is interested by my profile. Yes, and so what we can say about it, I don't know if I can say something, but yes, I will present my PhD defense on the 13th of October, and but in French. So I think maybe not people speak French on the Zoom now.
Very cool. So everyone who is interested in working with Florent, please reach out to him through Discord. And with that, let's thank all the speakers in this session again for the presentations of on the latest on input and interaction in mixed reality. I think this was really nice. And thanks also to the technical support during the session, so Michelle. And now that the talks are over, a quick reminder for everyone to join the post-session Q&A in GatherTown. You can directly interact with the authors there and ask your questions. Give it a try, it's a lot of fun. Michelle will also post a reminder how to get there from here. So thank you, everyone. I hope everyone enjoyed this and see you in GatherTown.